Hello, class. Well, I'd like to just talk with you today about Chapter 8 in terms of some of the solved exercise homework problems that you will encounter towards the end of this particular week. So, just kind of wanted to share work out some of the problems here, and I would just like for you to pay good attention to them because we do have a test next week, and I just want you to also be prepared as well. So when we are looking at our first question here is asking us how many electrons make up 1.75 Coulomb of charge. Keep in mind that an electron is nothing more than a negatively charged particle, okay? And it's been assigned a magnitude of 1.6 times 10 to the negative 19, and it has a negative sign, indicating it's a negative charge. Now, the relationship between the actual electric charge, denoted as Q, and the electron can be expressed in this equation here, whereby your charge is nothing more than the product of your number of electrons times electron value itself. Now, if you were to rearrange this equation and solve for the n, which are the number of electrons, we can actually find or solve this particular problem right here, number one. So we know that the charge is 1.75 coulombs, right? And then we also know that the electron itself is nothing more than 1.6 times 10 to the negative 19 coulombs. Of course, the coulombs will cancel out, and you'll be left with this value right here. Number two, an object has 8 million more electrons than protons. What is the net charge of the object? Again, we're looking at the relationship between electrons and charge. And this particular equation right here shows the relationship between those two entities. So we want to be able to find the net charge, which would be Q, and that would be the product of the number of electrons times the actual magnitude of the electron itself. So the charge in this case, of course, is going to be negative because electron, of course, is of a negative value. Number three, what are the forces on two charges? You have charge 1, which is 0.6 Coulomb, and charge 2 is 2.0 Coulomb, respectively, if they're separated by a distance of 3 meters. So here we have charge 1, charge Q1, charge Q2, and they're separated by a distance of 3 meters. Well, to kind of know where all this stems from, there's a relationship between like electrostatic forces. So the force, of course, that's going to be imposed on these two charges within a vicinity of 3 meters can be expressed using this particular formula, which would be the force times some constant, that K, which is expressed here, times Q1 times Q2 divided by the distance squared. And you can find that in equation 8.1. So, the actual force of repulsion, since they're two positively charged particles, there's going to be some repulsion. You can't, it's like trying to bring two South Pole magnets together. They're gonna repel because they're the same side. Okay, so by this being a plus and by this also being a plus in terms of their sign, there's going to be some kind of repulsion, as I have here. So we use this formula, and then we plug and play, and then we're going to get the force between them is going to be 1.0 times 10 to the 9 newtons. Now we have another question that's similar to the previous one you just solved just now. So find the force of electrical attraction between proton and electron that are this amount apart. 5.3 times 10 to negative 11. 5.3 times 10 to negative 11 meters apart. So we do know from our textbook, we know this value. We also know this value as well from our textbook. Likewise, we know the mass of the electron. We also know the mass of the proton. So put in that perspective, we can find the actual force, Coulomb force, and that's going to be, again, your constant K times the actual product of the charge of the proton and charge of the electron divided by r squared. And we're going to get this as our answer. Now, if you want to look at the gravitational force between these two entities, so you have the mass of the electron and mass of the proton, right? And this G is a constant, some gravitational constant, which is denoted here. When we start plugging in what is the mass of the electron, what is the mass of the proton divided by the distance apart, we're going to get the gravitational force is going to be of that value. So the ratio of the two, which is the actual Coulomb forces divided by the gravitational force, we see our ratio is a very, very high number. Okay. Now there's a net charge for number 5. There's a net charge of 4.8 times 10 to the 8 electrons by a point in a wire conductor of 0.25 seconds. What is the current in the wire? Okay. So keep in mind that current is nothing more than the flow of electrons or the flow of electrical charges. And there's a relationship between that flow, that current, and the actual charge itself. And it's being denoted here as I equals Q divided by T, T being time. So they gave us the actual number of electrons, and they gave us the time. So from there we can find our Q, right? We know that our Q happens to be 4. Our Q happens to be N times your electrons, right? So the number of electrons which was given to us was 4.8 times 8. 4.8 times 10 to the raised to the power 8 electrons. And we know the actual value of an electron, which is right here. It's the number of electrons here. We can multiply the two, and we can find the charge, the corresponding charge. And now we can find the actual current. Again, so your current is nothing more than the charge divided by the time. And once we find the charge, our Q, divided by T, we can find the actual amperage within that conducting wire. And this will be our answer here. Number 6, a current of 0.5 amps flows in a conductor for 6.5 seconds. How much charge passes at a given point in the conductor during this time? So they gave us the actual this must be 1.5 here. Made a mistake. So they gave us the current, 1.5 amps. They gave us a time, and they're asking us how much charge passes at a given point. So we can rearrange I equals Q divided by T. We can rearrange this formula to whereby Q, the charge, equals I times T. And that's what you typically see right here. Okay? Then we can find what our Q is, which is a charge. Number 7, an individual component with a resistance of 50 ohms is connected to a 120 volt source. How much current flows through the component? So this right here is dealing with Ohm's law, okay, which tells us there's a relationship between the voltage, the current, and the actual resistance within that component. So they identified to us what the voltage source was. They told us what was the resistance of that component. So from Ohm's law, we can find out what our I is. We can rearrange the equation, and then we find our I to be 2.4 amps. We have another question that's slightly related. Two resistors with values of 25 ohms and 35 ohms, respectively, are connected in series and hooked up to a 12-volt battery. The first part of the question is asking us how much current is in the circuit. Well, you kind of want to keep in mind when you're dealing with resistors, whether in series or in parallel. So when resistance or resistors, I should say, are in actual on series, just keep in mind that the current is always going to be the same. Okay, the same current is going to pass through all the different resistors. Now, the total resistance due to these individual resistors, right, that are in a series formation, you just typically add the resistance. So your total resistance is going to be R1 plus R2 plus R3. Okay, that's going to be your total resistance. So now if we wanted to be able to find the actual find the current that's going to flow through this particular circuitry, is going to be V divided by, in this case we have RS, just telling you and I that that's the resistance that happens to be in series. Okay, so keep in mind that when you're dealing with a circuitry that has resistors that are in series, your current is always going to be the same. I1 equals I2 equals I3 equals I4, on and on and on. And the voltage, always keep in mind there's always going to be a voltage drop. So the voltage across each resistor is going to be different. Okay, so just kind of keep that clue in mind. Okay, and this is how your circuitry will look whenever you have resistors in series. So once you find out what your current is, it's going to be V divided by the actual total resistance. Part B is asking us for the power, and the power is nothing more than the product of the current times the actual voltage. And you can find more information on that in page 209. And that's going to give us 2.4 watts. Number 9, we have two resistors with values of 25 ohms and 35 ohms respectively are connected in parallel this time. And they're hooked up to a 12-volt battery source. So how much current is flowing through the component? So again, keep in mind that parallel circuits, the voltage across each resistance is the same. Unlike the previous example, the voltage across each resistance is not the same. So here you have V, your voltage, happens to be the same throughout the whole circuitry. Now, just take a good look at, you see how your current here is all the same throughout the circuitry for a series circuit diagram. Here, your current is not the same. So the source of this current, it kind of splits up as it goes through each segment of the circuitry. So I1 is a combination or a summation of I is a summation of I1, I2, and I3. Also important to know that when you're dealing with resistance in a parallel circuitry, this is parallel to this circuitry, or this resistor is parallel to this resistor, is parallel to this resistor. Now the way you're going to actually find the total resistance is going to be 1 over the resistance parallel, the total resistors in parallel, equals 1 over R1 plus 1 over R2. And then once you do the math, you're going to get your total resistance in a parallel circuitry is going to be R1 times R2 divided by R1 plus R2. And then you're going to get 15 ohms as your total resistance that happen to be in a parallel formation. And once you find that, you can just divide it by, you can now find your current, whereby the voltage source divided by the resistance will give us 0.8 amps. Now, if you want to find the power, again, the same thing. We know that power is nothing more than the product of the velocity of the actual voltage times your current, which is 9.6 watts. Another example here, a 30 ohm resistor and a 60 ohm resistor in series are connected to a 120 volt DC, just means direct current source. The question now is asking us, what is the current in each resistor? Okay, so we have two resistors, resistor 1 and resistor 2. So the key is now that we know that since they are actually in series, we have to add them up to get the total resistance throughout the whole circuitry. So when you do that, you can now take your voltage and divide that by the total of those resistance, which is going to be 30 plus 60. And you get amps of 1.33 amps. Now, in order to consider the actual voltage drop, so we said earlier that the voltage for circuitry that's in series, the voltage across this resistance is going to be different than the voltage across this resistance. Okay, that's just the definition of resistors that are in parallel. Okay, now when we do that, since you already know that V1 does not equal V2, but we do know that I equals I1 equals I2, we can now take that same current that we just found here, and we can actually multiply that by each resistance. Now again, V equals IR. Okay, this is Ohm's law. We already found I, and now R is going to be different for each aspect of the circuitry. Now we can find our voltage too by just multiplying the current times the resistance, which we have here. And we get 40 volts and 80 volts respectively. Our last question is dealing with a transformer that has about 300 turns on its secondary and 100 turns on its primary. The primary is connected to a 12 volt source. You can find more information on page 230. Question A is asking us, what is the voltage output of the secondary turns? Okay. Now they gave us N1, which is number of turns, N2, which happens to be having another set of turns, which would be 300. Our V1, which is our voltage, happens to be 12 volts, and then the current is going to be 2.8 amps. Now the relationship between the voltage and the actual coil turns can be denoted here. V2 divided by V1 equals N2 divided by N1. So kind of keeping that in mind, I can solve for V2. And when I do that, I'm definitely going to get the actual voltage for those particular coils. Now B, if the current of 2.0 amps flow in a primary coil, how much current is in the second coil? Excuse me. Well, since there's a relationship between the voltage and the current, as the voltage and the number of coils, there's also a relationship between current and voltage. Okay, so now I can find my current in the secondary aspect of the coils. Just in this case, solve for I2. Okay, And when you do so, you're going to get 0.67 amps. So these are some of the questions that you'll be faced with on your upcoming test. If you have any questions, please just let me know and I'll be here to help you. Thank you very much. Bye-bye.